Diagonalization in linear algebra. In this video, I will discuss about the diagonalization in linear algebra, presented by C2 text. Diagonalization is an important concept in linear algebra that simplifies many matrix operations, such as computing matrix power, solving system or linear differential equation, and analyzing transformation. This guide provides detailed explanation of diagonalization, including definition, condition, step, example, and application. Okay, the next step. What is diagonalization? Diagonalization is a square matrix. A is diagonalizable if there exists an invertible matrix B and a diagonal matrix D, but invertible matrix B, diagonal matrix D, such like this, A is equal to PD P power minus 1, where A is the original matrix. A is the original matrix B is a matrix whose column are the eigenvectors or A, eigenvectors or A. Eigenvector or A. D is a diagonal matrix containing the eigenvalue of A. P minus 1, P power minus 1 is the number of P's. If a matrix is diagonalizable, its power, exponential, and other functions become much easier to compute. If a matrix begin mean that this sentence means that this sentence means that if the matrix A is the matrix diagonalizable, its power, exponential, and other functions become much easier to compute. Okay, why diagonalization useful? Computing matrix power efficiently. Instead of computing A power n directly, we can use D power n P power minus 1. Since D power n is easy to compute, each diagonal element is raised to their power, and the method is much faster. Solving linear differential equation, many differential equations in both matrix exponential like e power a if A is a diagonalization. E power A, P power D, P power minus 1. Understanding linear transformation. Linear if the transformation is represented by diagonalizable matrix. Its effect can be analyzed in terms of sample scaling along independent direction given by the eigenvectors. Condition for diagonalizability. If matrix A is diagonalizable, if and only if A has linear independent eigenvector, thus form a basis of R1, a matrix is diagonalizable. If and only if only has linear independent eigenvector, thus form a basis of R1 or C1 for complex matrix. For the key conditions, the matrix psi m into n is a diagonalization where if it has a linearly independent eigenvector. A matrix is diagonalizable if it has an distant eigenvalue, though this is sufficient, it is not necessary. If a matrix has repeated eigenvalue, it can still be diagonalizable if there are enough linearly independent eigenvector. In the next step, what is matrix not diagonalizable? If this is the explanation why a matrix not diagonalizable. If a matrix has fewer than and linearly independent eigenvector, it cannot be diagonalized if the algebra multiplicity number or time eigenvalue appear in the characteristic equation is greater than the geometric multiplicity number of independent eigenvector for that eigenvalue. Then the matrix is not diagonalizable. Diagonalized matrix for diagonalization in matrix, compute eigenvalue of A that determine A minus lambda I equal to 0 to find the eigenvalue of lambda 1, lambda 2 into to lambda n. Find the eigenvector for each eigenvalue. For each eigenvalue, lambda I is solved. A minus lambda I and we do V equal to 0 to find the eigenvector Vi for the matrix B and D. The matrix B A is formed by placing and the eigenvector as colon. The matrix D is formed by placing the eigenvalue along the diagonal. Verify that p power minus 1 8p equal to d. Finally, check that p power minus 8p equal to d. If this holds, then A is successfully diagonalized. So we're calculating for diagonalization a 2 into 2 matrix, 2 into 2 matrix, 2, 2 matrix. Consider the matrix A equal to 4 power minus 2, 1, 1. Firstly, we need to find eigenvalue that A. This is the formula that A minus lambda I equal to 0. And then we get the 4 minus lambda minus 2, 1, 1 minus lambda equal to 0. This is the sample memory for sample calculating current eigenvalues. Eigenvalue is like this, therefore determinant A minus lambda I equal to 0. So we put the A value 4 minus 2, 1 minus 1, 1, and then we subtract the lambda 4 minus lambda minus 2, 1, 1 minus lambda equal to 0. And then we solve this determinant 4 minus lambda 1 minus lambda minus 2 into 1 equal to 0. Like this, diagonally multiplying 4 minus lambda 1 minus lambda minus 2 into 1 equal to 0. After that, we get this equation lambda square minus 5 lambda black 6 equal to 0. After solving this equation, we got lambda minus 3 into lambda minus 2 equal to 0. And then finally, we get the lambda value equal to 3 and lambda 1 equal to 3 and lambda 2 equal to 2. Like this, lambda 1 equal to 3 and lambda 2 equal to 2. So, find and then we get eigenvalue, and then we can get find eigenvector. Lambda 1 if we play the lambda a1 equal to 3, a minus 3 into I into v equal to 0, and then we place the value and in here 3, 4 minus 3, 1 minus 3, minus 2, 1. And then we get 1 minus 2, 1 minus 2 matrix H1 column beta equal to 0, and then solving this one 1h minus 2 1 equal to 0. So we put the y value 1 equal to h equal to 2. This is the eigenvector column matrix of v1 equal to 2 1 for lambda 2 equal to 4. Replacing lambda 2 value or 2 equal to a minus 2i into v equal to 0. And then we can get the column factor 2 minus 2, 1 minus 1 into h1 equal to 0. So we solving 2h minus 2y equal to 0. And then we put the y value equal to 1. Then we can get the h value equal to 1. V2, so finally we get the eigenvector V2 equal to 1, 1 column matrix. And then form the value of P and D. For the P value 2, 1, 1, 2. D value equal to 3, 3, 0, 0, 2. And then compute the P and bar minus 1 equal to 1, 1 minus 1, minus 1, 1, 2. This is for like this. Diagonally change 1 and 2, and then we this diagonal value multiplied by minus 1 minus 1. This is changing 1 and 2 1 2, and then we get there p power minus 1 p inverse. So finally, if we satisfy p in bar a into p value equal to d, a is diagonalized. Finally, we can get that finally we can show the value is diagonalized. Application of diagonalization, computing matrix power efficiently, Fibonacci sequence, Markov chain, Probit system or linear differential equation, quantum machine and physics, graph theory, several application of diagonalization. Diagonalization very useful in the fields of quantum machine physics, agency matrix and graph, Fibonacci sequence, Markov chain. Conclusion. A matrix is diagonalization if it has a linearly independent eigenvector. The process involves finding eigenvalue, eigenvector, and constructing P and D. Diagonalization simplify matrix operation, making computation faster and more efficient. Thank you. Terima kasih.